Hi, my name is Zhezhen Wang. So in this project, my goal was to build a reliable classifier to predict the loan outcomes while maximizing the F1 value. So which means I have to balance the precision and the recall. I begin by creating a structured pre-process pipeline so that all data transformation were consistent and reproducible. These numerical values were input using median values and standardized, while categorical variables were input using the most frequent value and converted using one-hot encoding. To improve the model performance, I experienced with multiple uh, algorithms before selecting XGBooster as the final model. I compared the logistic regression, random forest, and gradient boosting approaches. Logistic regression only provide a simple baseline and help me understand the feature relationships, but it struggled with nonlinear patterns. The random forest improved the performance by capturing interactions, yet its F1 value was still very low. Um, so I choose the XGBooster method. The XGBoost produced the strongest result because it can model complex nonlinear relationships and handle mixed feature types effectively. Um, from a business perspective, logistic regression offer interpretability, while XGBooster provides stronger predictive accuracy, which is more valuable when trying to reduce the financial risk in this case. Um, the class imbalance was another important challenge in this dataset. So to address this, I use SMOTE to oversample the minority class and improve the model's ability to identify default cases. Importantly, SMOTE was placed inside the pipeline so that it was only applied to training folders during the cross-validation, preventing data linkage. I also adjusted the decision threshold instead of relying on default value of zero point 0.5 by searching across multiple thresholds and selecting the one that maximizing the F1 value. I was able to better balance precision and recall. This step significantly improved the performance because it aligned the model's decision with the competition metric and with the real business trade-off. To further improve the performance, after the first submission file, I applied a hyperparameter tuning using the randomized search CV. I turned parameters such as the number estimators, tree depth, learning rate, subsampling ratio, and column sampling. Random Randomized search allow me to efficiently explore a larger parameter space without excessively computation. After turning the model achieve a higher cross-validation F1 performance compared with the initial baseline, showing that the classifier were better optimized and more stable. I then returned the final model using the best parameters and generated another submission and get a better score. To assess the model fit, I used the stratified K-fold process cross-validation instead of a simple training test split. This validation strategy ensures that each fold preserved the class distribution and produced more stable performance estimates. I evaluate model behavior using out-of-photo predictions, which provide a realistic estimate of how the model would generalize to unseen data. The confusion matrix helps me interpret the um, prediction errors, showing the balance between uh, correctly identified safe loans and the detect risky loans. In a low-improved context, false positive represents approving borrowers who may default, which creates financial risk, while false negatives represents rejecting good borrowers, which reduce the business opportunity. So this curve further illustrates the trade-off between the capturing more defaults and maintaining precision, helping justify the threshold adjustment strategy. In the end, I would say if I had more time and the resources, I would improve the classifier by incorporating extra external data source such as microeconomic indicators, uh, credit burn data, or regional employment trends. These features could provide additional content about borrower risk beyond the variable currently available. Um, in a production setting, I would also implement ongoing model monitoring to detect performance uh, degradation and data drift. This would include tracking features distributions, monitoring key metrics such as F1 value over time, then triggering retaining when significant drift occurs. Overall, this project demonstrated how careful pre-processing, model comparison, class imbalance handling, validation strategy, and threshold turning can work together to produce a strong model for the prediction.